Good day everyone. In this video lesson, we will discuss about rings and fields. A ring is a set R is equipped with two binary operation plus or addition and multiplication, satisfying the following three sets of actions called the ring actions. It is an abelian group under addition, meaning that one, it is associative, or A plus the quantity of A plus B plus C is equal to A plus the quantity of B and C. For all A, B, and C in R, and we have A plus B is equal to B plus A for all A, B in R, or commutative. There is an element 0 in R such that A plus 0 is equal to A for all A in R. That is, 0 is the additive identity. For each A in R that exists negative A in R such that A plus negative A is equal to 0, that is, negative A is the additive inverse of A. R is a monoid under multiplication, meaning that the quantity of A times B times C is equal to A times the quantity of B times C for all A, B, C in R, that is associative. There is an element 1 in R such that A times 1 is equal to A and 1 times A is equal to A for all A in R, that is, 1 is a multiplicative identity. Multiplication is distributive with respect to addition, meaning that A times the quantity of A plus C is equal to the quantity of A times B plus the quantity of A plus times C for all A, B, C in R, left distributive, and we have the quantity of B plus C times A is equal to the quantity of B times A plus the quantity of C times A for all A, B, C in R, and that is right distributive. We have some properties of rings. First, the additive identity is unique. Second, the additive inverse of each element is unique. Another, the multiplicative identity is unique. And for any element x in a ring R, 1 has x times 0 is equal to 0 is equal to 0 times x. 0 is an observing element with respect to multiplication, and negative 1 times x is equal to negative x. If 0 is equal to 1 in a ring R, or more generally, 0 is a unit element, then R has only one element, and that is called the zero ring. If a ring R contains the element ring as a subring, then R itself is the zero ring. The binomial formula holds for any x and y satisfying x times y is equal to y times x. We have some examples of rings. We have integers with addition and multiplication, integers that are natural numbers with addition and multiplication, 2 by 2 matrices or the set of 2 by 2 matrices with matrix addition and matrix multiplication. We have real number x, the set of polynomials with real coefficients with addition and multiplication of polynomials, and many, many more. So since we're done with the rings, I will now give the floor to Miss Apple Jane Carion to discuss about fields, which is also a part of rings.
Okay, thank you, Miss Tabal. And for the field, formally, a field is a set F together with two binary operations on F called addition and multiplication. A binary operation on F is a mapping. F times F implies F. That is a correspondence that associates with each ordered pair of elements of F, a uniquely determined element of F. The result of the addition of A and B is called the sum of A and B, and it is denoted as A plus B. Similarly, the result of the multiplication of A and B is called the product of A and B, and it is denoted AB or A times B. These operations are required to satisfy the following properties, referred to as field actions. In these actions, A, B, and C are arbitrary elements of the field F. Okay, for the field actions, associativity of addition and multiplication, where A plus the quantity of B plus C is equal to the quantity of A plus B plus C. That is for the addition. For the multiplication, A times the quantity of B times C is equal to the quantity of A times B times C. Commutativity of addition and multiplication. A plus B is equal to B plus A. That is for the addition, and for the multiplication, A times B is equal to B times A. Additive and multiplicative identity, there exist two different elements, 0 and 1, in F such that A plus 0 is equal to A and A times 1 is equal to A. So that is for the identity property. Additive inverses. For every A and F, there exists an element in F denoted negative A, called the additive inverse of A, such that A plus negative A is equal to 0. For the multiplicative inverses, for every A should not be equal to 0 in F, there exists an element in F denoted by A raised to negative 1 or 1 over A. That is for the law of negative exponent, right? For the fraction. And it is called the multiplicative inverse of A, such that A times A raised to negative 1 is equal to 1. Distributivity of multiplication over addition. A times the quantity of B plus C is equal to the quantity of A times B plus A times C. The quantity of A times C. Okay, these are the example for fields. Integers, which are prime number, then rational numbers, real numbers, and complex number, and then rational number times square root of 2, which is a square root of 2 plus b, where b is an element of a rational number, and many more. Okay, for your assessment, you are going to show or prove that z integers is a ring, and prove that rational numbers times square root of 2 have identity.